Hello and welcome. Today, we're going to take a deep dive into a fascinating challenge at the intersection of climate change, food security, and artificial intelligence. How to accurately forecast crop yields, especially when the weather becomes extreme and unpredictable. Climate change is transforming agriculture. Extreme weather events like the U.S. drought in 2012 that cut corn yields by 13%. Or the 2019 floods that prevented planting on over 19 million acres are becoming more frequent and severe. In this volatile environment, accurate yield prediction is no longer just an academic exercise. It's a critical tool for managing agricultural risk, ensuring food security, and guiding policy. However, many of our current AI models for this task systematically underperform precisely when we need them most, when yields deviate sharply from historical trends. The authors of the paper we'll be discussing today attribute this failure to a fundamental data problem. There's a lack of rich, physically grounded datasets that directly link the complex state of the atmosphere to crop yields on the ground. To address this, they introduce a new framework called VITA, which stands for Variational Inference Transformer for Asymmetric Data. VITA is a novel pre-training approach designed to learn powerful representations from vast satellite-based weather datasets and then transfer that knowledge to the more limited ground-based measurements that are typically available for yield prediction. Let's unpack the core challenge that VITA is designed to solve. The authors term it the data asymmetry problem. On one hand, for pre-training, we have access to incredible satellite datasets, like NASA Power, which provide dozens of detailed meteorological variables, things like radiation fluxes, humidity, wind speed, and surface pressure. For example, the NASA Power dataset used in this work contains 31 such variables. This data is rich and comprehensive. On the other hand, when it comes to the actual task of predicting crop yield for a specific county, what we call the fine-tuning or deployment stage, we often only have access to a much smaller, more basic set of ground-based weather statistics. Think daily minimum and maximum temperature, precipitation, maybe 6 variables in total as used in this research. This creates a fundamental mismatch or asymmetry between the features available during pre-training and the features available during fine-tuning. Most general-purpose time series pre-training methods assume that the input features will be consistent between these two stages. This assumption is simply not true in the weather domain, and this makes existing approaches suboptimal. This data asymmetry problem is a key hurdle that has been largely unaddressed by prior AI models. This is where VITA comes in. It is a variational pre-training framework specifically designed to transfer knowledge from rich satellite data to limited ground-based inputs. The central idea is that since crop yields are largely governed by weather, learning a rich latent representation of weather states is essential for accurate forecasting. VITA uses a two-stage process. First, there's a self-supervised pre-training stage, and second, there's a variational fine-tuning stage. Let's look at the pre-training stage first. VITA uses a transformer encoder architecture. It's trained on the large NASA Power dataset, which covers 39 years of climate data. The model is given a sequence of weather data, but with a twist. It employs a technique called progressive feature-wise masking. This means that at each step, a random number of the 31 available weather features are hidden or masked. The model's job is to predict these hidden, detailed variables based on the ones it can see. This forces the transformer to learn the intricate physical relationships between different atmospheric variables. Crucially, this pre-training is variational. Instead of just predicting a single value for each masked feature, VITA learns to predict a latent atmospheric state, represented as a probability distribution, specifically a Gaussian distribution with a mean and a variance. The training objective encourages this distribution to be as accurate as possible in describing the true, detailed weather state. A particularly clever detail here is the choice of the prior distribution. In many variational models, a standard normal distribution is used as a prior, which is a simple regularizer. However, weather is not random. It has strong seasonal patterns. To capture this, VITA uses a seasonality-aware sinusoidal prior. This prior explicitly models the periodic, wave-like nature of weather variables throughout the year. It has parameters for amplitude, frequency, and phase that are learned during pre-training. This imposes a more structured and meaningful organization on the latent space, encouraging the model to learn representations that align with natural seasonal cycles. Now, let's move to the second stage, fine-tuning for yield prediction. This is where VITA's design truly shines, particularly with its decoder-free objective. Standard variational autoencoders, or VAEs, typically have two parts: an encoder that maps input data to a latent distribution, and a decoder that tries to reconstruct the original input from that latent representation. But the authors of VITA make a key insight based on meteorology. They argue that in this context, the decoder is unnecessary. Why? Because established physical principles and equations, like the Tetten's equation or the Penman-Monteith formulation, show that basic weather statistics like temperature and vapor pressure are deterministically linked to the more detailed atmospheric state. In other words, if you know the detailed state, you can calculate the basic statistics with very high accuracy. The authors empirically validated this, showing an MLP could reconstruct basic weather from detailed weather with an R-squared value greater than 0.999. Given this deterministic relationship, they model the probability of the basic weather given the detailed state as being approximately 1. This allows them to simplify the standard variational objective, completely eliminating the decoder term. The resulting fine-tuning objective has two parts. The first is a standard mean squared error loss, which measures how well the model's final yield prediction matches the actual ground truth yield. The second part is a KL divergence term. This term acts as a regularizer, ensuring that the latent distribution learned from the limited 6-variable ground data stays close to the structured, seasonality-aware prior that was learned during pre-training. During this fine-tuning stage, the model takes in the limited ground-based weather data along with historical yield data from the previous 6 years. This historical yield serves as a clever proxy for hard-to-measure local factors like soil quality and management practices, reducing the need for extensive auxiliary datasets. The pre-trained transformer encodes this information into a latent weather representation, which is then fed into a small multi-layer perceptron, or MLP, to produce the final yield forecast. The authors set out to test 3 main hypotheses. First, that pre-training on rich weather data improves yield prediction, especially in extreme weather years. Second, that their variational objective with the sinusoidal prior outperforms standard approaches. And third, that these benefits generalize across different time periods and conditions. To do this, they evaluated VITA on predicting corn and soybean yields across 763 counties in the U.S. Corn Belt from 1982 to 2018. They compared its performance against a comprehensive set of baselines. These included traditional methods like OLS regression and XGBoost, established deep learning models like CNN-RNN and GNN-RNN, which notably have access to soil data that VITA does not, and other state-of-the-art pre-trained models like SIM-MTM and the foundational model Chronos. To create a fair comparison and isolate the effect of their variational objective, they also included a baseline they call T-BERT. T-BERT has the exact same transformer architecture as VITA, but is trained with a standard mean squared error reconstruction loss instead of the variational objective. Any performance difference between VITA and T-BERT can therefore be directly attributed to the variational approach. The primary focus of the evaluation was on extreme weather years. These were identified as the 5 years for each crop with the largest deviation from the 5-year rolling average yield, years like the 2012 drought or the record-breaking 2004 season. The results are striking. In these critical extreme years, VITA with the sinusoidal prior achieves state-of-the-art performance. For corn, it reached an R-squared of 0.729, and for soybean, 0.722. This represents a significant improvement over the architecturally identical T-BERT, which scored 0.660 for corn and 0.693 for soybean. These gains translate to a reduction in prediction error of 2 bushels per acre for corn and 0.3 bushels per acre for soybean, a critically important margin of accuracy during severe droughts when billions of dollars in crop insurance decisions are on the line. The results also show that traditional methods fail catastrophically in these extreme years. For instance, the OLS baseline only achieved an R-squared of 0.27 for corn. Even advanced deep learning models that used soil data like GNN-RNN were outperformed by VITA, and the larger foundational models like Chronos struggled, likely due to the data asymmetry problem. Comparing the different versions of VITA is also insightful. TBERT with its standard pre-training provides a strong baseline. Moving to VITA with a standard normal prior already boosts performance by about 7%. Adding the seasonality-aware sinusoidal prior adds another 3% improvement, confirming that explicitly modeling seasonal structure is highly beneficial. Of course, strong performance in extreme years is only valuable if it doesn't compromise performance in normal years. The authors tested this by evaluating the models on standard years from 2014 to 2018. Here, VITA again achieved top performance, with an R-squared of 0.827 for corn and 0.837 for soybean using a 15-year training window. This confirms that the model generalizes well, and its optimization for extremes doesn't hurt its accuracy under normal conditions. The paper also includes several stress tests to assess the model's robustness. In one experiment, they simulated early season forecasting by cutting off the weather data at the end of July, before the harvest. Even with this incomplete data, VITA maintained strong performance, achieving an R-squared of 0.689 for corn, nearly 3 times better than the OLS baseline. In another test for temporal robustness, they trained the models on data from 1994 to 2009 and tested them on a forward-gapped period from 2014 to 2018. VITA again maintained its performance advantage, demonstrating that the patterns it learns are not just era-specific correlations, but are robust over time. To truly understand why VITA works so well, the authors conducted a series of ablation studies. One of the most compelling experiments explores spatial transfer. They pre-trained VITA exclusively on weather data from Central and South America, a region climatically distinct from the U.S. Corn Belt, with no geographical overlap in the training data. Remarkably, this pre-trained model still led to substantial performance improvements when fine-tuned on U.S. yield data, achieving a 34 to 37% gain for corn and a 17 to 19% gain for soybean over a randomly initialized model. This is powerful evidence that VITA isn't just memorizing local weather patterns. It's learning universal, physically grounded relationships between weather and agriculture that are transferable across continents. The authors also visualized the latent space learned by the models using principal component analysis, or PCA. The visualization for TBERT shows a highly compressed, collapsed latent space, where the representations for a good year like 2004 and a drought year like 2012 are not well separated. In contrast, VITA's variational objective, especially with the sinusoidal prior, creates a much richer and more structured latent space. The clusters for the 2 years are clearly distinct, and the variance is more evenly distributed across components. This indicates that VITA is learning a more powerful and expressive representation of weather, which enables it to better differentiate between normal and extreme conditions. In conclusion, the VITA framework presents a significant advance in crop yield forecasting. Its success stems from a domain-aware AI design that directly confronts the core challenges of the field. By using a variational pre-training framework, it effectively bridges the gap of data asymmetry between rich satellite data and sparse ground measurements. Its decoder-free objective, grounded in physical principles, and its seasonality-aware prior, which captures natural temporal structures, allow it to learn robust and transferable representations of weather. The practical implications are substantial. The authors note that VITA's 3.2x improvement in R-squared over the OLS baseline for extreme corn years translates to an 11.4 bushel per acre reduction in prediction error. Across the nearly 90 million acres of the Corn Belt, this level of accuracy improvement represents billions of dollars in value for programs like the Federal Crop Insurance Program and for guiding policy responses during climate crises. Furthermore, because VITA relies only on publicly available weather and yield data and is computationally efficient, training end-to-end in under 2.5 hours on a single GPU, it is a practical and scalable tool for real-world deployment, even in data-scarce regions. Finally, the core idea of a decoder-free variational framework for asymmetric data has potential well beyond agriculture. It offers a promising blueprint for any domain where one can train on rich sensor data but must perform inference with a more limited set of sensors, from patient monitoring in an ICU to industrial IoT applications. This work highlights how thoughtful, domain-aware AI design can overcome fundamental data limitations and provide powerful tools to help us adapt to a changing climate.